Clearly, we have a problem in the network, and it's probably MTU related. Let's see if we can resolve it before continuing. By default, IS-to-IS will pad its hello packets up to the interface MTU. This is a crude MTU enforcement mechanism that prevents IS-to-IS from forming neighbors if full-sized packets cannot be sent. You can technically disable this behavior by removing the hello padding, but I generally leave it enabled for safety. Let's enable debugging on those hello packets using the command shown, and we'll limit the output to the VLAN 30 interface. I've disabled debugging after a packet was sent. R10 sent an IS-to-IS hello or IIH message on VLAN 30 with a length of 1496 bytes. After adding 3 more bytes to account for the logical link control or LLC encapsulation, the total packet is 1499 bytes. This is 1 byte shy of the actual 1500 byte MTU, but it's close enough and suggests that our end-to-end MPLS MTU is insufficient. This begs the question, what is the correct value? We could blindly configure a huge value, like 2000, which would quickly solve this problem. I want to take a more analytical approach instead. Let's think about the maximum encapsulation required. VLAN 30 has 14 bytes for Ethernet, 8 bytes for 802.1q because there are 2 tags at 4 bytes each, and a 1500 byte layer 3 payload. That's 1522 customer bytes. The MPLS transport adds a VC label, an LDP transport label, and a control word, each of which is 4 bytes for a total of 12. That results in 1534 total bytes, not counting the core link Ethernet encapsulation. We don't account for that in the MPLS MTU because it's at a lower OSI layer. We should configure it network-wide on all MPLS core interfaces. I've done that behind the scenes, and we'll verify it on R4. Just like for IPv4 and IPv6, we can control the MPLS MTU using this command. Now, R4 can send MPLS packets up to 1534 bytes out of this interface, which is just enough to account for the Layer 2 VPN customers' traffic. Remember, those customers are allowed to send 1500 byte Layer 3 packets, whether IP or CLNS, along with up to 2 VLAN tags per our design. Suppose the MPLS MTU isn't configured on an interface and you want to discover the default value. You can query the MPLS interface using the detail keyword using the command shown. At the bottom of the output, this command reveals the MPLS MTU, which we've statically set to 1534 bytes. On the topic of MTU, there's one more important aspect. Let's examine the VCID details for circuit 100 and filter on the word local. The access circuit MTU is signaled using targeted LDP and must match between peers. You can set this under the XConnect stanza, but this is seldom required unless you have a special use case. When the MTU doesn't match, the pseudo-wire cannot form, and the callout shows an example of that output. The VC status is down, and the MTU mismatch is reported. It is signaled as a local access circuit fault, and to troubleshoot it, just keep reading the output until you see the local and remote MTU values. The mismatch becomes obvious and is easy to fix. Let's head to R10 to ensure IS-to-IS is functional now. Right away, we see 3 log messages indicating that new IS-to-IS adjacencies have formed with R18 after our MPLS MTU adjustments were applied. We can further confirm it by checking the IS-to-IS neighbors. This looks better as we see 3 entries, 1 per subinterface, and all have the state of up. As a final check, let's query the routing table for all IS-to-IS routes to ensure R10 load shares across all 3 paths. Since we didn't modify the IS-to-IS metric, they are equal cost. R10 has 3 paths to R18's loopback, 1 via each subinterface, so I'm confident our EPL configuration is working.